Two antennas can be operating at the same frequency, using the same power, and pointing at each other and still communicate poorly. Why? The answer often has nothing to do with frequency or power. Instead, it depends on a property called polarization, one of the most important concepts in antenna and RF engineering. In previous lessons, we learned that electromagnetic waves consist of electric and magnetic fields propagating through space. We also saw that these fields are perpendicular to one another and to the direction of wave travel. However, this description does not completely define the wave. An important question remains. If the wave is traveling forward, in what direction is the electric field actually pointing? Does it remain fixed, rotate, or change orientation over time? The answer determines how effectively antennas can transmit and receive energy. This becomes especially important in wireless communication systems. Even when two antennas operate on the same frequency, mismatched field orientations can significantly reduce received signal strength. Understanding this phenomenon requires the concept of polarization. Polarization describes the orientation and behavior of the electric field component of an electromagnetic wave as the wave propagates through space. Since the electric and magnetic fields are always perpendicular, engineers typically define polarization using the electric field. The magnetic field orientation is then automatically determined by the laws of electromagnetism. The most common types of polarization are linear polarization and circular polarization. In linear polarization, the electric field remains aligned along a fixed direction, such as vertical or horizontal. In circular polarization, the electric field continuously rotates as the wave travels through space. Intuitively, imagine shaking one end of a rope. If you move your hand only up and down, the resulting wave has a vertical orientation. If you move your hand side to side, the wave has a horizontal orientation. The direction of motion determines the wave's polarization. Physically, consider a vertically mounted antenna transmitting a signal. The antenna generates an electromagnetic wave whose electric field is primarily vertical. A receiving antenna that is also vertically oriented can efficiently capture the energy. However, if the receiving antenna is horizontal, much less energy is received. Mathematically, polarization describes the trajectory traced by the electric field vector at a fixed point in space. The field may remain along a straight line, rotate in a circle, or follow an elliptical path. These behaviors correspond to linear, circular, and elliptical polarization, respectively. Polarization is critical in RF engineering because antenna performance depends heavily on polarization matching. Maximum power transfer occurs when the transmitting and receiving antennas have compatible polarizations. Many terrestrial communication systems use vertical or horizontal polarization because antenna design is relatively simple. Satellite systems often use circular polarization because the relative orientation between transmitter and receiver can change continuously. At the system level, polarization affects communication range, signal quality, interference levels, antenna design, and link reliability. Engineers carefully select polarization schemes to optimize performance for specific applications and operating environments. Polarization provides another way to characterize electromagnetic waves beyond frequency and power. Two waves can have identical frequencies and amplitudes while behaving very differently because of their polarization properties. A common misconception is that polarization only matters for antennas. In reality, polarization influences propagation, reflections, satellite communications, radar systems, wireless networks, and many other RF applications. Proper polarization alignment can significantly improve communication performance. As electromagnetic waves travel through different environments, they often encounter surfaces and obstacles. These interactions can alter wave behavior dramatically. In the next lesson, we will explore reflection of waves and discover what happens when electromagnetic waves strike a boundary or surface. In this lesson, we learned that polarization describes the orientation and motion of the electric field within an electromagnetic wave. We also saw how polarization matching affects antenna performance, communication efficiency, and wireless system reliability. In the next lesson, we will explore reflection of waves and discover how electromagnetic waves behave when they encounter surfaces and material boundaries. If you found this useful, like the video, subscribe, and follow for the next lesson.